So today what we're going to go over is Rolle's theorem. Now Rolle's theorem is the ability for us to take a function and prove that an extrema exists along some interval or between two different numbers. And a couple criteria exist on how exactly we go about doing that. The first and the most important is the fact that the left and the right side of whatever graph we're looking at have to be equal. So if I draw a line straight across, the two endpoints have to be at the same y value. So no matter how many points exist between there, we see the fact that the left and the right side are equal in their height. The other thing is that the graph has to be both continuous and differentiable between these 2 points. We can't have any gaps, we can't have any removable discontinuities, any jumps, any asymptotes, anything like that. So we notice that all of these graphs all are continuous. You can put your pen on one point and drag it without picking it up all the way to the next point. Now you might be doing a lot in the middle, but the idea is that it is continuous and differentiable. So let's go ahead and take a look at some examples. Now, before we even begin, let's take a look at what we're going. We're going to graph a sketch in our TI-84 right here, and we're going to state if Rolle's theorem can prove the existence of at least one maximum or minimum and state why. So we're not actually proving where the maximum or minimum exists. We're going to prove that if it can be stated. So the first and most important point on any one, let's go ahead and officially start on number 1. So the first and most important part about solving for Rolle, or about using Rolle's theorem, is the left and the right have to be equal. So your first step, actually let's do this in purple, is that f of -1 and f of 1 both have to produce the same output. So if I plug in a -1, that is the absolute value of 1 over -1, which is 1. If I plug in a +1, that's the absolute value of 1 over +1, which is also 1. So I know that it meets the first criteria. Both the left and the right side are equal in value, which means this thing is going somewhere and then coming back to it, which would imply that maybe a critical value or relative extrema exists. So then we're going to take a look at the sketch of the graph. And what you might have noticed is that in this first one, this isn't going to be a fully differentiable graph. So let's zoom out a bit. So that way we can pop this thing in here. And let's pop this into our calculator. So we go over to the y tables and I say math, go over to numbers, absolute value of 1 divided by x. Now I'm only looking at it from -1 to 1. So I'm going to set my window from -1 to 1 and take a look at what this graph does. And so we notice something's going on up there. We might want to, if you're unfamiliar with this graph, maybe extend it up to, let's say, 100. But even with that, what we notice is the graph, if I could zoom in a little closer, this graph is going up, 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 and up, and coming back down. And you'll notice that this is actually a rational function, which means that there is an asymptote that exists right here in the middle. So albeit you might be tempted to blindly just apply Rolle's theorem and say left and right are equal, so therefore a relative extrema must exist, we notice that the asymptote prevents that from happening. So, no. So Rolle's theorem does not apply. Does not apply because an asymptote exists. So I can't use it for anything. Awesome. Let's try number 3. So number 3, hopefully this one will work and we'll find out that yes, it does. But our first thing is we're going to try out plugging in a 0 and plugging in a 3. Our first thought, if we want to prove does a relative extrema exist, I have to prove left and right are equal. So I'm going to plug in an f of 0 and I'm going to plug in an f of 3. Now if I plug in a 0, that's -0 squared, which is 0, and then 3 times 0 is 0. So I'm hoping the next one will get me a 0. Let's see, 3 squared is 9, and then the negative, so -9 plus 3 times 3 is 9, that will also get me a 0. So I know Rolle's theorem should technically apply. The only thing I'm going to check for is, are there any sort of asymptotes, holes, or jump points along the graph? So what we're going to do is we're going to come and we're going to sketch it. So let's clear this out. And we have a negative x squared plus 3x. And we're going to go from, in this case, from 0 to 3. I'm going to set my y scale back to 10. Boom. And so we notice that, yes, there are no holes, there are no asymptotes, and in fact, the graph makes a nice little shloop, little jump right there. So Rolle's theorem is met and a relative extrema could exist. Actually, not could exist. The whole point of Rolle's theorem is that it must exist. It is both continuous, differentiable, and both the left and the right sides are equal. So boom. So now that you've seen how one that doesn't work, because an asymptote exists along there, and one that does work, go ahead and try out number 5. Pause the video and pause it when you're done and see how well you did. Okay. So now that you've had a shot at it, let's go ahead and try it out. Our first thought should be, let's plug in our two values. So I'm plugging in f of 0 and f of 2 pi. So I know the sine of 0 and the sine of 2 pi. Let's see, sine of anything is the y divided by the radius. The sine of 0 radians is going to be 0. And 2 pi is just one loop back. So I know that left and right sides are equal. What I then need to check for is to make sure there's no asymptotes, holes, or jump points in the middle. So let's take a peek at what the graph would look like. We're going to set our y value, clear this out, and we have the sine of x. Now we know what the sine of x looks like in general, so let's go ahead and set this to 2 pi. I'm also going to double check my mode, and make sure my mode is in radians. Yep, and so let's take a peek at that graph. And that's exactly how we thought it would look. So from 0 to 2 pi, we have a sine wave that does that, continuous, differentiable, no holes, no gaps. So again, we know Rolle's theorem. So Rolle's theorem is met, and a relative extrema must exist along the interval from 0 to 2 pi. Awesome. So now that brings us to a different style of question. Here we go. So now these style questions are no longer determining if Rolle's theorem can exist, can prove it. We want to actually find where it does happen. But it does give us a nice little out, because if Rolle's theorem says that nothing can be found, then we have an easy out to say, well, it's not because we can't solve the math, it's because the conditions aren't met. So let's go ahead and take a peek at number 7. So number 7, again, the first thing that we always want to try out is plugging in those values. So we're going to plug in f of 1 and f of 3 and see what happens. F of 1 will give us, let's see, that'll be a 0 times negative 1 times negative 2, which is 0. F of 3 will give us a 2 times 1 times 0, which is 0. So first condition is met. The next thing that we want to try out is we want to try out to see, would the graph work? So let's go ahead and plug it in just to double check visually what's going on with the graph. Now, typically this won't be a technology problem, but we're going to go ahead and use it as right now just to make sure that we are applying in the right standard. This will end up being a polynomial, so it should work out perfectly fine. So x minus 1, x minus 2, x minus 3. and we're looking at the window from 1 to 3. And that's really tight, can't really see what's going on, so let's make that from a -2 to a +2. And so we see here that yes, it does verify that our calculations are correct, and we should have 2 relative extrema, one here and one here. So now our job is to hunt down and find those. So now that the conditions are met, and we have a nice little, I'm going to go ahead and draw the sketch, which looked something like this. We're going to section this area off and find what the derivative of that is and when it's equal to 0. Now this derivative, I've got a polynomial. It's not in standard form, so we're going to have to do a little bit of legwork to get it ready for that. Otherwise, I'd have to use the product rule once and then again, and I just don't want to do that. So let's go ahead and FOIL this. So that'd be x squared minus 1x minus 2x. -1 times -2 is +2. I'm going to distribute that x minus 3. So my first thought is to distribute the x and then distribute the -3. Yep, so +2. So we have 9 and then 6, yep. So if I add those values up, I get f of x is equal to x cubed minus 6x squared, 11x minus 6. So I'm trying to find the derivative of this, which is much easier to find than a product rule. Because the derivative, let's do this. Actually, let's swap over to green. So the derivative is 3x squared minus 12x plus 11. And we get that. I want to find when this is equal to 0. So I should get 2 values. We notice it's a quadratic, so I'm expecting the quadratic to give out 2 answers. So let's go ahead. If it's set equal to 0, I'm not going to worry about doing the 33. I'm just going to go ahead and plug this into the quadratic formula. So -b plus or minus the square root of b squared minus 4ac, so that's 12 times 11, which is 132, all over 2a, which is 6. Okay. So this will spit out x equals 12 plus or minus the square root of 12 all over 6. That I can pull out square root of 4 and square root of 3. Square root of 4 is 2, which will allow all this reduced. So that's going to be x equals 6 plus or minus the square root of 3, all divided by 3. Because once I factor out the square root, they're all going to divide by 2. So now what I'm going to do is I'm going to test out plugging in that point into the original function and into the derivative. If I plug it into the derivative, this should get me 0 both times. If I plug it into the original function, I should find this point and this point. So let's go ahead and let's try that out. So let's zoom out just a bit so we can try this. We have our original function already plugged in. So let's go ahead and plug in our other function. So 3x squared minus 12x plus 11. And let's plug in these two numbers. So 6 plus the square root of 3 divided by 3. Our derivative gives a value of 0, and it spits out our y value. So we know that okay, we have a c value of 6 plus the square root of 3 over 3 checks out. And we have another c value, another critical value, where it's going to be 6 minus the square root of 3 divided by 3. Again, it spits out our value right here. Actually, hold on. We're looking at values between 1 and 3. Both our values are between 1 and 3. That is one of the things you do want to check, is that this answer, when you find the derivative, might give us the value for a 0 outside of your interval. But if you notice, both of our values are between the rates of 1 and 3. So it's between the rate of 1 and 3. Yep. When we plug it in, they're both confirmed. They give me a 0 value, and that would be my y value. So I could put comma 0.3849. I could put comma negative 0.3849, and that will give me that point and that point. That's all we need to do. So let's do one more where we actually find the value. So let's take a look at tangent. Now, the first thing on Rolle's theorem that we want to do on number 9 is we want to plug in g of 0 and g of pi. So the tangent, I think that was an f that I just drew. So tangent of 0 and the tangent of pi. So tangent we know is y over x. Y over x of 0 is going to be 0. Of pi, it's also going to be 0. So the left and the right sides are equal. However, we should remember that tangents, when we graph them, have lots of asymptotes. So we're trying to check out, is there an asymptote between 0 and pi? And unfortunately, the answer is yes, because between 0 and pi, albeit that is a period, we do have an asymptote right in the middle. So Rolle's theorem does not apply. Does not apply because an asymptote exists at x equals pi over 2, which is within our interval. So unfortunately, we can't do anything with number 9. Okay. And so that brings us to the last one, number 11. So go ahead, now that you've seen where it works and where it doesn't, pause the video, try number 11, see how well you do, and pause it when you're done, and check it out. Okay, so let's try this one out. Our first look is we're going to say, okay, let's do this, keep in the theme. So we're going to plug in h of 0, and we're going to plug in h of 2. So h of 0 is going to give us a nice big, let's see, 0 squared minus 0. E to the 0th is going to be e, or not e to the 0th is going to be 1, sorry. 0 times 1 is going to be 0. When I plug in the 2, 2 squared is 4 minus 4 times e squared. Well, 4 minus 4 is 0. So that's going to net out 0. That checks out. If we want to double check our graph, make sure it looks continuous. Let's go ahead and clear these out. Clear that out. We're going to get an x squared minus 2x times e to the power of x. And we're going to take a look at that graph from 0 to 2. Let's expand this back to our negative 10 to 10, just to make sure we see the whole thing. Okay, and that looks perfectly fine. We know between 0 and 2. Looks like the graph is relatively flat, and then it pops back up. So now between those two values, we should get 1. Possibly if this is flat, we might get a second one, but we're not exactly certain on that front. So let's go ahead and start the process. If we start the process of finding where that critical value is, we're going to find the derivative and find where that derivative is equal to 0. So h prime of x is what we're after. Now right here, I see that I have a product, so I'm going to go ahead and say u is x squared minus 2x, and v is e to the x. U prime would be 2x minus 2. V prime would be e to the x. Now the first thing, when we go ahead and find the derivative, we notice that both of them are multiplied by an e to the x. So h prime of x is equal to, let's see, e to the x times 2x minus 2 plus e to the x times x squared minus 2x. So with this derivative, we're trying to set this derivative equal to 0. So if we set this derivative equal to 0, I can factor out an e to the x and say, hey, if e to the x equals 0, we have one answer. And then if whatever's left over, so if 2x minus 2 plus x squared minus 2x, that would also work. We know e to the x, no matter what number we raise e, it will not exist. Which means that we're probably looking at something that's right here. So no worries on that front. This one we're just going to go ahead and combine terms. So that'll give us an x squared plus 2x minus 2x, which in this case, we have a positive and negative 2. Now, just like on number 7 where we said we have to check our values, when x equals positive 2, that is within our range. But x equals negative 2 is not within our range. So the only number we're testing is, does the positive square root of 2 check out? Because we know the negative square root of 2 does not check out. It's not within our given interval. So let's go ahead and try that out. So we're going to come over here. We have our original function. Let's go ahead and plug in our derivative. So I'm going to plug in the full thing. We have e to the power of x times all of this. Actually, we know that this cancels or simplifies down to x squared minus 2. Come over here to our table, and I'm only going to plug in the square root of 2. Boom. Yep. We see that, yes, it does produce a value of 0 for the derivative, so I know that that is the flat point. And if I wanted to find the actual point on the graph, well, then this point would be the square root of 2, comma, this, negative 3.408. But this one has been verified, and there we go.